notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos, sections 1, 2, and 3. These 3 sections here. All 51 of those videos have been published in their entirety on YouTube. Section 4, measurement. All 17 of these videos have been completed. 5 have been published in their entirety on YouTube. Section 5, statistics. All 18 of these videos have been completed. 5 have been published in their entirety on YouTube. Section 6, algebra. We are now on the 21st of 22 videos in this section and should finish this section by the end of this month, September. After that, we go on to section 7, relations, functions, and graphs by October 2025, and then section 8, geometry and trigonometry by November 2025, and finally section 9, vectors and matrices by the end of this year. Disclaimer down here, this schedule is just a projection and it is not to be interpreted as a contract with anybody. In trying to make this video as short as possible, I will quickly scroll through most of the typical introduction, since you have already seen this in other similar introductions. So I am quickly scrolling through most of the introduction. Section 6, algebra. We finished most of it. So we are now here. We have finished objective 17, 18, and 19. Those, and we are now at objective 20, this one here, which we will get done in video 21. So we finish 20 videos in this section. These indicated in yellow have been published in their entirety on YouTube. These others are only partially published on YouTube. And since this is video 21 down here, this will only be partially published when it is finished. So as I said, we are now at objective 20, which says represent direct and inverse variation symbolically. And we have some explanatory notes down here. Y varies directly as x, and that is shown as y varies directly as x, or y is equal to kx, that's direct variation. And then inverse variation, y varies inversely with x, that's 1 over x, or y is equal to k over x. We will find out later on that there may be a little problem with the meaning of this. Just a reminder, this is the Greek alphabet, uppercase A, lowercase a, and beta and gamma and so on, delta. We have seen that before. And theta for angle, and lambda for wavelength, and mu for micro. But we are here. The lowercase Greek letter a means varies in these formulae. So this letter here, which is this symbol here, but we wouldn't say alpha. We would say y varies directly with x, or y varies inversely with x. So firstly, let's deal with direct variation. Y varies directly with x, or y is equal to kx. Now, if you have a little equation like this and you say y is equal to 2x, and you use various values for x and you get the various values for y, and you plot a graph, this is what the graph looks like. Direct variation: as one quantity increases, the other also increases by the same difference. Example, hours worked with wages. So wage is directly proportional to the hours worked. Direct variation: as the x-axis increases, the y-axis also increases by the same amount. So that's direct variation. Now let's look at several of these on the same graph. So y is equal to x, y is equal to 2x, y is equal to 3x, y is equal to 0.5x. If we plot all of those on the same graph, we get this. This one here, as you could see, is y is equal to x, and so on. In all graphs of direct variation, the lines or the graphs slant to the upper right, moving from left to right. So as you move from the left-hand side of the graph to the right-hand side, the direct variations always slant upwards. How steep the slant of the line is depends on the gradient. In these cases, those would be the numbers in front of the x. For example, y is equal to 2x, or y is equal to 3x, or y is equal to 1x, or y is equal to half x. Those are the gradients, and those indicate how steep the lines are. The increases are directly proportional by a factor of k. So y is equal to kx, and we could work out what k is. It would be y over x, which is the gradient, increase in y over increase in x. So if we draw a perpendicular up here, it's a perpendicular, and we consider this one here, notice we have a triangle here. We could find a gradient, which will be increase in y over increase in x. Increase in y here is 8, increase in x is 4. You divide 8 by 4, you get 2. That's a gradient. Or you could take this green line here. Increase in y is 12, divided by increase in x, which is 4, and so you get 3. And so on. 4 divided by 4, you will get 1 for that one. And this last one down here, 2 divided by 4, and you get half. So this k here, which is a constant, yeah, I know. We could have spelled it with c, but c represents something else. So k here represents a constant, like we can't spell. Anyway, let's go on. We will come back to this inverse relationship just now. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. So let's take a brief overview of inverse. In inverse variation, as one quantity increases, the other one decreases. Example, the percentage charge remaining on your phone to the hours of use of your cell phone. The more you use it, the less percentage charge you have. For example, let's use some numbers here. Let's say your phone charge would last for 13 hours, more or less. So at 0 hour, it is 100% charge. And after 13 hours, it is only 2.5% charge. If you plot that on a graph, you get this graph here on the right-hand side here. This graph here. That's an inverse relationship. As one increases, as a time increases, hours of use, the percentage of charge that remains decreases. Now let's take a closer look at that. And this is the table used. Now, if we use this inverse formula here that we are given, we have a problem. The problem is that that formula does not work for inverse linear. Now, CSEC did not specify that there are two types of inverse that we need to look at. One is inverse linear, and this formula does not work for inverse linear. Now, this is the formula for direct, and that works. So that red line there shows direct relationship. The blue one shows inverse. That formula does not work for inverse linear. So if you were charging it and it took that amount of time to charge, let us say 4 hours to charge. Let us say 4 hours to charge. We could see a direct relationship there, direct linear for charging. But when it comes to use, we have an inverse relationship. But this formula, as I said, that we are given here does not work for this situation, for inverse linear. As another example, consider time traveled in minutes and distance from home. Distance from home. If you plot that on a graph, you get this graph you see over here. It is an inverse linear. I am stressing the word linear because we will find out that the formula we are given does work for inverse, but not inverse linear. Inverse variation, as one quantity increases, the other one decreases. Distance to home, not distance from home. Distance to, and the time traveled. The more you travel, the less distance you have to reach your home. Now, if we were dealing with distance away from home, that would be a direct relationship because the more time you travel, the more distance you cover. But here we are talking about time traveled and distance to reach your home. So as you travel more, the distance decreases. And as I said, this formula that we are given here for inverse relationship does not work for inverse linear. And I will explain that later on in this video. If we were going the other way around, distance traveled from home on that red line, then yes, this direct relationship formula that we are given here, y is equal to kx, does work for that direct relationship. All right, so let's look at some more direct relationships. Question 1. The wage W of an hourly worker depends on how many hours worked, H, and the hourly rate, R. Write a general algebraic expression showing the relationship among these three. Wages would be directly proportional to hours worked, or wages is equal to hours worked times the rate. And so you could say W is equal to R times H. So we have just represented a direct variation symbolically. W is equal to RH. Now, if you need to find K in this formula, which is R, then K is equal to Y divided by X. Now, inverse relationship K is equal to Y times X. So let's look at this example. If two men can build a house in 100 days, let's say that is D, then 4 men will build that same house in 50 days, working at the same rate, and 8 men working at the same rate will get the job done in 25 days. So now D is equal to 200 over M if we substitute in that formula that we are given there. Unlike the two previous linear graphs that we just saw, this one is inverse exponential, as we will see on the next slide, but not linear inverse. And yes, this formula here does work for inverse exponential, but not for inverse linear. Here's a table. 2 men took 100 days, 4 men 50 days, 8 men 25 days, and so on. We plot a graph, and this is what it looks like. Now, this does not look like an inverse linear. It looks like an inverse exponential, and yes, this formula does work. And so we get the formula D is equal to 200 over M, D being days, M number of men. That 200 came from one man will take 200 days. So we can use that formula depending on the amount of men available. So inverse exponential, that formula does work. If you double the independent variable, that would be the number of men, and that results in 1/2 the dependent variable, that would be the number of days, you will get an exponential graph as you see over here. And as I said, this formula does work for that. So this one on the left here is direct variation. If you need to find k in y is equal to kx, then k is equal to y divided by x. Fine. Direct, always a straight line. Now, inverse variation, if you need to find k in this expression that you are given, then k is equal to yx. But note that that results in an exponential curve, not a straight line slanting down to the right. If k is equal to yx, the graph will always be exponential, like this. It will not be the opposite of this one you have on the left here, like coming down like that. It will not be that.